You clicked this video because you have heard the promise that robots will soon be as cheap and scalable as the software that runs them. The reality is far more complex, and the stakes involve the very feasibility of autonomous systems in the real world. By the end of this explanation, you will understand why physical intelligence faces a non-linear cost curve that prevents it from scaling like language models. There is a prevailing myth in the industry known as the software-defined robot. It suggests that if we just feed enough data into a neural network, a robot will learn to manipulate the physical world with the same ease that a large language model generates text. This idea is seductive because it implies that the barriers to entry are purely computational and that we are only waiting for more compute to unlock universal robotics. But this view fundamentally misunderstands the nature of physical interaction. When we move from the digital domain to the physical world, we encounter a wall that no amount of semantic scaling can simply push through. The core of the problem lies in the difference between semantic scaling and physical scaling. Large language models operate on a foundation of text, which is essentially infinite and cheap to generate. You can scrape the entire internet to train a model on human language. In contrast, physical intelligence requires what researchers call analytic concepts. These are mathematical procedures that enforce the laws of physics rather than just learning statistical correlations. A robot does not just need to know that a cup is heavy. It needs to understand friction, deformation, and the nonlinear dynamics of how that cup interacts with a surface. Here is the thing that breaks the software-defined robot narrative. In the digital world, errors are cheap. If a language model generates a slightly odd sentence, the system continues to function. It tolerates high failure rates because the cost of a mistake is negligible. But in physical tasks like manufacturing or autonomous navigation, the tolerance for failure is effectively zero. A single miscalculation in friction can result in a dropped part, a damaged product, or a safety incident. This requirement for near-zero failure tolerance means that the compute required to reduce prediction uncertainty to safe levels scales exponentially rather than linearly. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This divergence is confirmed by neural scaling laws for embodied artificial intelligence. While robotics does follow power law scaling, the coefficients are significantly steeper than those in language models. This means that for every incremental improvement in performance, you need a disproportionately larger increase in data and compute. The efficiency gains are significantly lower than in natural language processing because the cost of generating valid physical interaction trajectories is so high. You cannot simply scrape the web for examples of a robot successfully picking up a crumpled piece of foil without crushing it. Those examples are rare, expensive to generate, and require high-fidelity simulation. Consider the sim-to-real gap, which is perhaps the most notorious bottleneck in this field. In a simulation, you can run millions of trials in seconds. You can reset the environment instantly. But when you move to the real world, you face nonlinear dynamics like friction and material deformation that are incredibly difficult to model perfectly. The simulation is never a perfect mirror of reality. Because of this, the smooth performance gains seen in language models do not translate to the physical domain. A robot that performs perfectly in simulation may fail catastrophically the moment it touches a real object because the physical laws it learned in the digital twin do not account for the subtle variations in the real world. This creates a situation where the cost of reliability grows non-linearly. As you push for higher precision and reliability, the resources required do not grow at a steady rate. They explode. Practitioners note that without integrating structured physical priors, neural networks cannot achieve the controllability needed for critical infrastructure. Purely data-driven approaches are insufficient for complex physical interactions because they rely on finding patterns in data, and the data for rare physical events is simply not available at the scale required to train a robust system. The fundamental learning mechanism of large language models involves generating non-Gaussian outputs from Gaussian inputs. This is ill-suited for physical laws, which are deterministic and bound by strict constraints. Physical AI systems must rely on expensive, high-fidelity data collection and simulation rather than the cheap, infinite internet-scale text data that drives language models. This scarcity of valid physical interaction data means that as you try to scale to new tasks, you hit diminishing returns much faster than you do in text generation. So, does physical intelligence scale at all? The answer is yes, but with a critical qualification. Recent studies indicate that physical AI does scale with increased resources, but the barrier is not a fundamental impossibility. It is a prohibitive economic one. The resource intensity curve is so steep that infinite scaling becomes economically unviable without a paradigm shift in how we acquire data and how we design our learning algorithms. We are not facing a wall that cannot be climbed, but a mountain that requires a different climbing strategy than the one we used for the digital planes. The distinction is clear. Language models scale efficiently with data because the cost of adding more data is near zero. Physical AI faces a steep resource intensity curve, where the cost of reliability grows nonlinearly. This prevents the infinite scaling seen in the digital domain. We are moving from an era where we hoped software could define the robot to an era where we must engineer the robot to respect the physics that define it. The future of robotics will not be won by those who can train the biggest models, but by those who can best integrate analytic concepts with data-driven learning to navigate the nonlinear cost curve of the physical world. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.